now, between now and the end of the class, we're going to have some speakers from industry coming. So today, we are going to discuss codes and standards. They are very funny because I don't know very much about them. But that's what you're going to use the most if you ever go to industry, right? So, but it's my great fortune that here we have Dr. Niren Barnes, right, from Supreme Steel, and Curtis Bell from Iris NDT. To both of you, both of them, I suggest you smile because those are companies that eventually hire people. I don't know what the current situation is, but that's their, right? And so Niren did his PhD with us, and Curtis did his PhD with us, his master's with us. Right, and Niren is going to talk about the codes and standards in general, but with a focus on construction. These welding symbols, everybody loved in the first exam. He sent it to us, huh? Right? But those were the real ones, and so we wanted to start bringing the game closer to reality. Curtis will talk about the codes and standards as they relate to pressure vessels, and is that right? To pressure equipment, right? Which is different codes and standards. And between the two, they make pretty much all our life in the province. So it's very different than everything we have discussed so far. I have people who live and die by that, so you're very fortunate. That note, do you need a pointer or something? Would you like to?
No, I think I'm good. I can point with my fingers and talk.
All right, let's get started.
All right, so it's welcome. So yeah, like Patricia said, I'm going to give you kind of a brief introduction to codes and standards in general. I'll go through some of the pipeline and pressure vessel codes just in terms of to name some of the big highlights of them. I'm going to let Curtis, who's the expert in that side of life, do the deep dive into the examples, and then I'll go deep into what I know, which is the structural codes, the construction and general building stuff. So a little bit of background on what Supreme does, to know where I'm coming from. Supreme Steel is the largest privately owned fabricator and erector for structural steel in Canada. We've built many of the bridges, probably been delayed by our construction around Edmonton, all the Anthony Henday bridges, the 17th Street Bridge on the Anthony Henday that's being built, Ring Road around Calgary, those kind of bridges were all out of our shops. Big buildings, Bow Tower in Calgary, the Amazon Spheres down in Seattle, some of the big towers down in the States. We've built a lot of those big infrastructure and commercial building projects. So we have a long background in that, and some of the companies that we've actually purchased, we have a history of about 100 years or so in the structural steel and construction business. So lots and lots of history. So if you ever have questions about that industry, I'm your guy. Feel free to email me, ask questions. I'm always available. If it's about pressure vessels, pipelines, anything else, call Curtis. I'm not going to have good answers for you. I might have some answers, not good ones. Since you brought it up, I'll talk about the drawing that you guys had to do on your exam, which, sorry if it wasn't fun. That's my life. That particular drawing was super interesting for us as a project. So I'll tell you where it came from. That was off of a giant forestry overhead crane. So in the logging yards that they have, like essentially logs piled about 60 feet high and however many kilometers long, they have a giant overhead portal crane that lifts up all of those logs and moves them around and takes it off all the trucks and all that stuff. And we were building a new crane for a company. They had two cranes in operation, one that was a little bit older than the other one, and that one they went to do an inspection and the whole thing was cracked all the way through. So they did immediate termination of work and started on the new crane that mimicked the other one. They inspected the other one. We had previously built that about 17 years ago, and so that was what that drawing was. So it was unnecessarily complex, apparently, but it was a real life example. So, kind of Patricia already mentioned, all welding procedures and just sort of procedures, all welding in general falls into three main categories in Alberta. So we have pipeline, we have sort of the plant facility side of life that Curtis is going to dive deeper into, then we have the building structural side of life. And you'll find some examples of outside of that, but you don't find a lot of automotive, anything like that out here in Alberta. So some of the drier stuff, and I won't lie to you, codes and standards is not super exciting. It's reality in life. When you get into the industry, you're going to be looking at these and have to deal with them in some way, shape, or form. We'll try to not make it too boring and try to give you some real life examples, so at least you go out of this with some experience and some knowledge. So there's the dry and basic definitions here. So standard being more just a technical set of instructions or definitions that help designers and people who are implementing the actual welding on the shop floor in order to do their jobs. And then this is sort of a loose definition. You can find about 1 million different definitions of code versus standard. Standard becomes a code when it's adopted by a governing body, or it becomes more official. Multiple different governing bodies enact it. One of the really important things that you'll often not hear mentioned in the same sentence as codes and standards, but are often almost more important, is specifications. And specifications are kind of private documents by companies or certain industries that provide a more in-depth or more requirements along the way that are specific to that particular job. So you can have your codes and standards, that's your baseline, you have to do that in a job. Specifications are what make things more complex, and you'll see that as we go through. Specifications sort of tie the hands of the fabricators a lot of the time, because that's what they're being handed, and that's the absolute rule. Is somebody's coming to you, your client, and saying, this is my Bible, I don't care about what the codes and standards say, this is my Bible. So you have to do both, so it makes things a little more complex along the way. Codes are a necessity in the industry, whether people like it or not, and the reason for that is that it's how you kind of enforce that accountability and how you provide that quality guarantee. Now, obviously, there's no guarantee that even though you applied all the codes and all the standards that you're going to get a quality product at the end of the day. You still need to have that workmanship aspect, which is why you have people who can actually do the work, which is not me, but the actual welders on the shop floor. Those are the guys that you still need to have up to snuff. But it's kind of always looked at as a limit on the contractor, and that's one of the things that I like to highlight, is that it's not a limit on the contractor. If you are smart about the codes, you understand the codes and standards and the specifications you're being beholden to, you can actually use those in your favor to save yourself time and money in the long term. And that just takes that understanding. And not building a weld procedure that is only going to be good for one job, but maybe building a weld procedure that you can use for all the jobs that are coming up, or opening yourself up for new bids just on how you develop it if you're smart about it. Now, in codes and standards, we have to talk about governing bodies. Governing bodies, depending on the different industry, will have a different range of involvement. Some governing bodies never get involved. Organizations like the American Welding Society in the States, I'm sure you've heard of it, they govern pretty much all welding that happens in the States in terms of structural side of life. They never get involved. They're not a governing body that reviews anything. All the onus is on the individual contractor to do their due diligence. Whereas you have that same version in the Canadian market, which is the CWB, the Canadian Welding Bureau, and they are overly involved. Everything that you do in terms of a weld procedure, anything else, has to go through them. You pay them atrocious amounts of money. Everybody gets really upset when somebody says we have to submit something to the CWB, but it's just reality, right? So it depends on where you are, what code you're going into, and also what industry you're in. So if we talk relevant codes for the pipeline industry in Canada, really the name of the game is Z662. That is oil and gas pipeline systems. Here's a nice little cover page. I don't know if this is even the current version of the code anymore.
2019.
2019, there you go. So this became mandatory in Canada based on this onshore pipelines regulation, National Energy Board, Pipeline Act. This became a mandatory thing. If you're going to build a pipeline in Canada, you have to adhere to this code. The only exceptions get into weird things where you're going across the border, but then you kind of have to obey by both codes. So you don't get any favors out of that, you just have to do more work. These are some of the ones that I wanted to highlight over here. These are actually about different components of pipelines, so flanges, different valves, those kind of things, all have to adhere to their own standards. So this is sort of the main pipeline welding one, and then there's subsections, one of those. We go to plants and facilities, and the CSA version of this is the B51, which is the boiler, pressure vessel, and pressure piping code. That really isn't the name of the game, especially in Alberta. That is just sort of the code that's there. You have to follow it, but I believe, and Curtis can correct me if I'm wrong, but I don't think that's the big standard that everybody's trying to follow. So when you actually go into what people are looking at in this sector is the ASME boiler and pressure vessel code. So if you've heard the word section 9 or anything like that, that's where that comes in. We'll go into that in a second. And then the B31 code is sort of the design code. So B31.1 and B31.3, we'll dive into what those are in a second. Those are all relevant codes. And then the American Pipeline Institute, API, you have some of these different codes in here. And these ones that are pulled out are relevant because these are pipeline inspection codes. Those ones that I pull out here are actually more about how you get inspectors qualified and what the inspection requirements are for the pipeline. So, now you get to see a bunch of little names on the page. I've highlighted the ones that are more or less the most important sections out of this boiler pressure and vessel code. ASME Section 9 is the one that you will hear more than any other one in industry just because it is the welding standard. You'll also see some other things in there, non-destructive testing, materials, all those things have their own section. This code is an absolute behemoth of a thing to go through. Has lots of cross-references throughout it. I don't live in this world and I'm not that sad about it. So, if you have more questions, I'm sure Curtis is going to go into more detail on this. Now we go into the B31 code. You have B31.1 process piping and then B31.3 power piping for the first one, then process piping for the second one. And those are the two that you'll hear referred to the most often. Really the difference as I understand, again, not the expert, but the difference as I understand is power piping one has a lot more general rules on pressure piping industry, a lot less specific, and then once you go to B31.3, that's where you're talking a lot more of the facility specific things, a lot more small grade ways to go about it. And then they also have some different versions for pressure piping. It's worth noting that they have liquid and gas pipelines in here, but these are not sort of the same thing that we're talking about when we're talking about the Z662 applicability. It gets super confusing. I'm not going to go into the details of it, but essentially your code is still going to be dictated by the industry that you're in. So don't get too worried about it unless you end up in one of those industries. And finally, structural. So the stuff that I actually know very well. In Canada, you'll hear CSA 47.1 and W59. Those are kind of the all out there codes, where 47.1 is the governing code on certification, so that certifies companies, certifies welding procedures, certifies welding personnel, everybody, all of that is detailed in 47.1. And then W59 is actually how you weld steel. So it gives you all of the requirements for actually applying the procedures that you've built in the first code. S16 is an important one. S16 is design of steel structures. S6 is Canadian Highway Bridge Code. So those design codes don't really have a whole heck of a lot of information on welding. Some of the references are in there though, that's more so just design. And then when you go to the American side of the code, the important ones that you hear is D11. So D11, actually 47.1 and 59 are more or less, if you combine those and put them together, they're D11. In the past couple of years, D11 has actually somewhat gone a little bit behind what the Canadian codes have, and the Canadian codes have kept up very well, but they're more strictly applied, so it's a little bit different. Bridge welding code, this is my personal nemesis in my job. D15 governs all welding for bridges. Alberta, for some reason or whatever, even though S6 is the highway bridge guide, and you normally just have to apply to this and that for those top two, for building a bridge in Canada, Alberta is by far the industry leader in bridges, and so they said the D15 code is more stringent, we're going to use this as our baseline code. And then somebody like 10 years ago decided D15 still wasn't stringent enough, and then they came up with specifications. And the specifications, if you ever go into anything with the bridge industry, you'll hear the term Section 6 and Schedule 18, which are these awful bridge welding codes where they took D15 and they essentially put on steroids. And very, very stringent regulations. And then this last one is an interesting one, not so much relevant here, but very relevant to projects that are done in sort of the Northwest and North America, is the seismic welding code. That's very, very important. And actually, a speaker that Patricio has had in a couple of times, Dwayne Miller, or Dr. Dwayne Miller, has a lot of experience and actually was one of the former founding members of the seismic code and the reason that it came into existence. Essentially realizing that you can't just design a building the same. If you are going to experience earthquakes, you need to design it with those considerations in mind and how that affects welding. Now we get into some of the weirder stuff about welding. So WPS to a lot of the welding industry in Alberta means Weld Procedure Specification, and that is the document that you hand to the welders and essentially says, you're going to do this weld, here's how you do this weld. That's what that means for a lot of the different industries. Ironically, my industry, the structural industry, that's not what that means. WPDS, which we'll get into once we get into the structural side, but if you ever hear me accidentally say WPDS, I'm not doing it on purpose instead of WPS. In the structural code, Weld Procedure Data Sheet is that paper, And then weld procedure specification is actually not how to do the weld, it's okay, how do you weld anything that you're doing metal core with? So it's a process-specific document. So if I mess up, that's my bad, but it is confusing because for some reason the structural guys decided they didn't want to be like the rest of the world and made a different name up. So I'm kind of pre-programmed to do that. But more or less, a WPS is a document that you should be able to take, hand to a welder, and the welder should know, based on that, what parameters they're using, what process they're using, all of those different things to produce a satisfactory weld that meets all the requirements of whatever code you're doing. Some of these are pre-qualified, as in, you look at the code book and it says, okay, if you do X things, you follow these parameters, you do these kind of things, you just go ahead and weld. You don't need to do anything special. Here's a data sheet, have the class. Most of the ones that we actually deal with in the province require what's called a procedure qualification record. So that's testing that you do, and destructive test or non-destructive testing in order to prove that your weld is going to do what you say it does, right? So, a little bit of a tricky one there, but the pre-qualified section, while it seems super awesome, is only really applicable to the structural industry. In other industries, you won't see too much of that. Mostly you need to do this testing and do a PQR in order to get it out there. So, I put up this flowchart. It's more or less true. Some people are building weld procedures and start at different points along here. But more or less what you should be doing is trying to determine first off where you are, what code you're under, what you're building, and then start to build your weld procedure based on that. So are you going to need to do testing? What materials and filler metal do you want to use? What is that going to look like in terms of the joint? Okay, what parameters are you going to physically use for welding, which you guys have started to dig into in this course? Then once you've done that test, how are you going to evaluate if that weld was good or not? Then you're going to write what that test record looked like. Then you're going to actually write your weld procedures, and then you're going to submit it to approval, whether it's just to a client or to a governing body. It kind of depends on the code. But this is sort of the basic flow chart. I like this flow chart, but like I said, certain people start at different points where they say, okay, I need to use this material, and instead of breaking it down and planning it out properly, they might start somewhere along that process and try to get to the same place at the end. And sometimes you can miss things or not really plan it out the best to best suit your needs going forward. So we'll start off these two sections. I'm going to go through pipeline weld procedures first, then I'm going to go through some of the boiler and pressure side of life. I'm going to try and go through those sections relatively quickly. Like I said, Curtis is going to go in more in depth on the pressure side especially. And all of these codes, the similar lessons can be learned throughout them. Many of the things that you'll hear, they might differ from code to code in terms of what the specifics are, but many of the terms will be the same. And then finally, I'll go into the structural side of life, and then we're going to go through a pretty in-depth example on how to build an actual weld procedure. And I have a weld procedure that we developed in-house, and how we went about developing that, we'll go through step by step. So, as I mentioned, Canadian Pipeline Code Z662. In this code, there are really no pre-qualified weld procedures, none of relevance. So it means that you have to do testing for all of your weld procedures, which means that when you go into a job, if you want to start on time or be economical in any way, shape, or form, you better have that planned well in advance and not be going to a job expecting to do the testing as part of the job startup, right? You want to be able to get going as soon as you go, so oftentimes you'll need to be doing this as you're bidding work. Depending on how big the pipeline is, obviously for huge projects, it's going to take years for that to come, so you got time. Very often these will go through review and approval by the contractor or the owner. There aren't really a lot of governing boards that are going to review this for you. You are kind of beholden to what your customer and the engineers of your customer know. The term you'll hear a lot is engineer of record. You'll hear that no matter what industry you're in or where you go in engineering. Engineer of record means the responsible person. So who did the design? They're making the call. Very often the engineers of record are specific to that industry. So if you're building a building, it's going to be a civil engineer. He might know absolutely nothing about welding, but it doesn't matter. You have to convince them that whatever you're saying is right. For pipelines specifically, there is this kind of third party, the National Energy Board, and I think, definition-wise, I got to remember this one. I think this is the Energy Resource Council Conservation Board.
It's now the AER, the Alberta Energy Regulator.
There you go. Even a better answer. So these guys are essentially government-run, national government or either provincial or federal can come in and do reviews, especially if they're asked to do an audit. They can come in and do reviews of your weld procedures. And even if a client has said yes, these guys can come in and say this doesn't look up to snuff or it's not obeying code. You need to look at this. So those are things to be aware of when you're actually building pipeline well procedures. I put some different things in here. We're not going to go through everything in detail. It's just not worth any of our time to do. Materials that are allowable for pipelines and the pipeline are all shown in this particular clause within the code. All the different components, the flanges, valves, those kind of things are also listed in this code. One of the things that I did want to highlight in here, because it is important to working in Alberta, and you will see this pretty much everywhere, and it shows up again and again through all the different codes that we go through, is this idea of notch toughness. And I think you guys did Sharpie testing or saw Sharpie testing maybe? No?
You familiar with Sharpie testing?
Everybody knows the big hammer comes swings down and gives you energy? So that concept is extraordinarily important in Alberta. Rightly or wrongly, people feel that it is the governing test that solves all problems. If you can pass impact energy tests at low temperature, you're good to go. That's right, again, rightly or wrongly. In some ways, it is a very good thing. You want to make sure that your whatever you're building can stand up a low temperature service. That shows up in every single one of these codes we're going to look at today. And it shows up very, very prevalently because we're in Alberta. Especially when you go into northern Alberta where pipelines are built. You're talking operating temperatures where it kind of sounds like, oh, it never gets to minus 40. Well, sometimes it gets to minus 60 up there. So the operating temperatures that they're working at are that low. The confusing thing about this is that notch toughness is very often termed in categories or different categories of notch toughness, but it means something different in every single code, which is super confusing, but it's the way that it is. So in this particular code, I'll just highlight, essentially, it means that if you have a category 1, it means that you have a pipe that needs no impact requirement. So it doesn't have any low temperature requirement, it's fine, it's good to go. This one, category 2, is sort of the more stringent of these, where you not only need to have a Sharpie or equivalent impact energy, but you also need to look at the fracture surface to see what that looks like and evaluate whether or not it's exhibiting the type of fracture that you'd like it to be, right? So is it ductile, is it brittle, that kind of thing. And then category 3 is the one where you're just proving it based on impact energies. And most of the other codes that you'll see, the categories are not broken down like this. For example, the structural codes, the categories for different levels are temperatures and impact energies. So a category 3 in a structural code actually means that you just need to have impact energies 27 joules and minus 30 degrees C. And then when you go to category 4, it's just a different, it's actually ironically the same impact energy, it's 27 joules, but it's just at a lower temperature, so it's minus 45 degrees C. And we're starting to see a lot more of those requirements go that way, whether it's needed or not. All the design codes that are out there all have operating temperature charts. So if you're building something in Edmonton, if you're building something in Calgary, it'll tell you what the average temperature is and what you should be designing around. But design engineers are very, very risk adverse and like to build in safety factors. So oftentimes you'll be building something in Calgary, even though it doesn't really get into operation at very, very low temperatures, you'll still be required to go to the most stringent version of it just to build in that factor of safety. So sometimes you can fight it, but very often their word is the law, so you have to live with that. Now, clause 7 is where you actually start to get into the nitty-gritty of the welding procedures in Z662, and this lists essentially all of the necessary information that goes into a weld procedure. So there's lots of different things that go into it. What welding process are you using? Whether are you using it in a mechanized way, or are you doing it by hand? What is the joint that you're actually building? So is it those lovely welding symbols? Is it a V-groove? Is it a bevel groove? Is it a fillet? What are you building? What are your base materials you're welding on? So if pipeline you're talking, are you building an X70 pipe, an X80 pipe? Filler metal, so that will depend on your process. So fluxes might be applicable if you're doing like seam welding with subarc or something like that. Shielding gases, again, process dependent. And then you have your position and direction of welding. So are you welding it out of position, like in an overhead position? Are you doing it vertical? And are you going towards yourself, away from yourself? All those things start to matter. We have preheat temperatures, interpass temperatures, and then post-weld heat treatment. Seem like additional requirements, but all of them need to be listed on weld procedures because both of those things affect the final properties of the weld, and that's what you're expected to be designing your weld procedure based off is what those final properties are. And then you get into the stuff that Patricio knows more than anybody about is the electrical characteristics. So you actually have to go through in a lot of codes that will list what can you actually vary in terms of all the different types of parameters when it comes to welding. And that goes through everything that you guys will have looked at this year, and maybe some things that you guys haven't really looked at in depth this year, like pulsing, those kind of things. All those things affect where your final weld properties are, and you have to take them into account. And then finally, technique. And technique is very often sort of glossed over in terms of people not really thinking about it. They think, oh, if I have these parameters, I'm going to make a good weld. Well, depending on how you pattern those welds, depending on how you do your layer buildups, all those different things start to matter. One of the biggest things that I saw very, very early on in the industry was the difference between stringer beads and non-stringer beads. So what a stringer bead is, essentially you put a bead on a plate or in a groove and you run it. You don't do anything fancy, you just run it straight along there. The other thing you can do is you can weave, right? So you can get into that joint and you can go back and forth, and it allows you to essentially build up a much bigger weld and maybe a little longer, but not that much longer. And one of the biggest things that I saw very, very early on in the industry was the difference between a stringer weld and a weave weld. In terms of weave welds looking really, really pretty, but very often being false positives. Essentially, you get a weld that looks gorgeous on the outside, and then you actually go and test it, and it's absolute crap throughout. Because when you weave, you leave holes, right? You leave holes all over the place, and you get lack of fusion throughout. And so stringer beads, while welders hate them because they don't look nice, actually are very, very effective. So one of the biggest things you'll ever see in welder tests is you'll never really see anybody weave in a welder test unless it's specifically required for that test, because it's not an advantageous way to pass a test, right? So it's very, very, just kind of a one-off thing, but very, very important. And this is another one of those things like notch toughness that I wanted to highlight, essential variables. Essential variables will come up in every single code. Essentially what an essential variable is it affects your procedure qualification test. If you change an essential variable outside of the range stipulated in the code, you're going to have to redo your procedure qualification test. So this is one of those things that you need to, the first thing you should do in a code, in my mind, is once you know what the code is about, is you need to go familiarize yourself with the essential variables. Because if you're going to design a weld procedure to a certain code, if you know those essential variables and how they're controlled, you can actually do yourself a lot of financial and time good in the long run by taking those into account and not neglecting them. Not just saying, okay, I need to do this one specific thing right now, I'm going to design my weld procedure to do this one specific thing. You want to take the essential variables into account and say, okay, if I do this test, this enables me down the line to do a couple more things. And essential variables are very real detailed. So in this particular code, we'll go through the essential variables for all the codes. But for this particular code, they have, they're shown in table 7.3. And so I have pulled the entire table 7.3 into this presentation. We're not going to go through it line by line. I put it in here just to show you what kind of things are in here. But essentially you can see already it varies on the size of pipe that you're doing, or whether or not you're doing it with essentially automatic welding, so mechanized welding or not. And those are the three things. And whenever you see an X in this table, it means that that's an essential variable for that particular subsection. So you can see that there's things about joint geometry in there, the carbon equivalent of the base material. There's all these things about thickness, and thickness is always a really, really important thing. So you want to take that into account. You want to do your testing to know, look, where am I going to be qualified based on this? And there's lots of tables in there that will tell you this information. This is just the essential variable side of it. OD, you have your welding consumables composition, you have your size of your filament material, and then you have your different welding position things. All of these things are different essential variable examples. And like I said, we don't need to go through it in a lot of detail. It's just there to show you guys what this looks like. But you'll see this in every single code. And essential variables are, in my mind, the most important thing you can familiarize yourself with in a code, because that's what gives you the power to use the code for you and not just to meet your client's requirement. All right. So that was essential variables. All of the ones from that table are shown in there. But what I want to do now is start moving through some of the PQR testing stuff. So this code is actually a very good highlight of some of the different tests that you have to do. So when you do a procedure qualification test, based on what you're trying to qualify, so different sizes of pipe, and then what it'll do is it'll tell you what types of testing that you need to do. So you see up here, there's tension testing, nick break, root bend. We'll go through what these are in just a second. I have examples of all of these. But essentially it's going to tell you exactly, if you want to qualify a procedure and you want to be qualified for those sizes of pipe, these are the tests that you're going to have to do. So some of these got tests, and actually, here's even better, they show you on the pipe exactly where you need to extract these samples from. And Z662 is very good about this. And all the codes will show you in a different way, and I'll show you a little bit later the structural side of this. but it'll show you exactly where you need to do this. And the reason for these selections is actually very intention, that has a lot of intention behind it by the code designers, essentially wanting you to extract samples from your pipe at places where you're likely to have the worst properties, right? So when you're down here, you have some of the ones where you should have good properties, but you also have them from down here where you might have some of the worst properties as you're coming down. The automated welding is a little less prevalent because they've made a lot of efforts to take account for that, but with manual welding, if a guy is on top of a pipe like this, it's a heck of a lot easier for him to weld. As he goes underneath that pipe, it's going to get a lot more difficult. So, first testing method that we're going to highlight here is tension testing. I'm sure you guys have seen a tensile test at some point if you're all materials engineers, I'm guessing, probably. These particular ones, when you do a groove weld test, or you're extracting your groove weld specimen, so you're taking that little cross section of the little pipe element. For this particular coat, you don't actually remove the weld reinforcement. So you leave that weld reinforcement on, and then you put this sample in there and you pull it, and if it achieves the correct tensile strength, then your weld is good to go. Essentially what you're looking for here is that your weld doesn't fail at low tensile strengths inside of your weld or inside your has. If it fails in your base metal, quite frankly, that's even more concerning because it means you're using bad pipe, but it shouldn't be happening by the time you get to this stage of doing a PQR test. The nick break test is one that's fairly just isolated just to pipeline, and that's one where you actually use a saw blade and you cut into your specimen on either side, and then you either break it through tensile testing or you break it through hitting it with a hammer. And the whole point of this test is to look at these fracture surfaces. And if that fracture surface looks like what you want it to, then you proceed forward and say the nick break test was a success. Bend tests are we're going to highlight them in two different sides. So root and face bend test. Essentially you're bending around the top, so the face of your weld, or you're bending around the root of your weld. And either way, essentially the pass-fail for this, the criteria is written in the code, but the pass-fail is essentially you want to be able to bend the sample in a specific jig. So essentially you put it into a jig that looks like a giant U, and I'll show you one in a second, but you put it into a giant U and you have another piece that fits into there, you'll put your sample on top of that and you'll press it down, essentially forcing a bend around your weld, either on the root or the face, and that will either stay perfectly fine and just kind of bend and look like it's normal steel. You'll still be able to see your weld, but it'll just bend nicely. Or, in the bad cases where your PQR is going to fail, it's going to actually separate. Either it'll separate in the middle of the weld, or it'll separate in the has. But that's what the purpose of this test is. And then we also have the side bend. And so side bends are exactly what it sounds like. Instead of bending around this axis or bending around this axis, you're going to bend around the side axis of it. And side bends are common in all codes. Structural code, for instance, doesn't do root and face bends very often whatsoever, but side bends happen all the time. And those, same thing. It'll just tell you whether or not there's failures based on if there's separation when you bend it. So this is this bend test specimen that I was talking about. We actually put the plate in there, press down, and you produce the shape out of it. And there's some samples where you can't really tell because it's just a picture. But this specimen is actually like a horseshoe, right? Like it's complete U. So it's just stood up on the side. And there's a nick break one in the middle. Just pressing down on it. So I said I was going to go quick through pipelines, weld procedures. That was pipeline weld procedures. So it is just a brief overview. I just wanted to give you guys some of the highlights and talk about some of those common things that you'll see, like notch toughness and essential variables throughout the rest of the codes. So we're going to go through plant and facility weld procedures. Again, I'm going to go extra fast because this is what Curtis is going to dive deep in. But I'm just going to get you familiar with some of the terminology so you know what you're looking at. So like I said, most of this qualification comes out of ASME Section 9. I believe that there are pre-qualified weld procedures, but essentially in Alberta they're completely useless because everybody wants a PQR or wants to use the low temperature. So very often you have to do weld procedures for this, and this qualifies all the different kinds of operations that you would use on a pressure vessel or pressure piping. And then you also have some additional design requirements from the construction codes, like the B31.1s and the B31.3s. Now, these are going to go through approval by the owners, the contractors, similar to how the welding procedures did for the pipeline weld procedures. But there's also jurisdictional authorities that come into play here, and particularly in Alberta, you'll hear the word ABSA the second that you get into the industry. ABSA is the Alberta Boilers Safety Association, and they essentially hire a bunch of, or employ a bunch of engineers that review weld procedures for a living. And you can ask Curtis, but I think there is some strain between industry and ABSA at certain times. They're a little bit stringent on their requirements. So they don't like to let any of the contractors get away with anything. So if you operate in Alberta in this industry, I'm sure you'll become very, very familiar, probably too familiar with all this. So in this code, so the welding part, this section 9, there's a couple different articles that I wanted to highlight here that essentially detail all the different aspects of weld procedures and weld procedure qualification. So this first article is the welding requirements. So this goes through basic welding positions, the different testing requirements, so different types of destructive testing, all those types of things are all listed in here. But this is just sort of an informatory clause. This article talks about the generalities of the welding side of it. Then you get into Article 2, which is actually weld procedure qualification. This is going to tell you a little bit about what test coupons you're going to need. It's also going to go through your welding variables in detail. And like I mentioned before, this code, just like the previous code, is going to address essential variables in some way. They add in this extra little caveat called supplementary essential variables, as well as non-essential variables. In the other code, non-essential variables are just anything that aren't listed in the table. So if it's not listed in the table for the pipeline code, it's a non-essential variable. Here they actually go through and define what those are. And then the other thing that's interesting, and I don't know if you guys have covered this in your class or not, but they actually go through and define around temper bead welding. So temper bead welding is sort of what it sounds like. You weld in such a way that your current pass actually tempers the bead that came before it. So you're affecting the microstructure in a very specific and designed way by welding on top of it with the next weld. So as the section I actually goes through and defines how to do temper bead welding and the restrictions that are placed on that. And you can get some very, very interesting weld properties by doing that process. I'll skip you there. Essential variables, so I just wanted to highlight what these mean here. So essential variables is, again, same sort of definition. If you change any of the ones listed there, then you need to do a new PQR. And some examples are welding process, joint design, base materials, those kind of things. And filament metal, all those things would also fall into that line. Now, this code chooses to do the notch toughness as a supplementary essential variable, and that's something that will very often be specified in Alberta. And then finally, you have the last one, which is your non-essential variables, which is essentially anything that's not listed up here, and they actually go through and list what it is in this approach, which is nice. And those are things like welding parameters within reason, right? You still have to work with what you've done in your test. You just allowed some sort of ranges in there. Here's a giant list of words that list all the welding processes that you're allowed to use within this code. I'm not going to go through in detail, you have it there if you'd like to go through, but it covers all the ones you would have seen in your class and all the ones you guys would have done. Plus some ones that actually you guys are very, very lucky to have seen, like laser beam welding, those kind of things, which I know the laser's still not quite operational, but it's almost there. And then electron beam welding, it's all covered in this code as well. So then Article 3 is the weld performance qualifications, and that is all about the welder testing. So it'll give you all the information on the coupons required in order to qualify your welders and welding operators, and it also gives you how long your testing is good for all those things. So one thing that we don't talk about that much in this presentation is the fact that even though you have to qualify your welding procedures, you also have to go through and qualify all of your welders or welding operators along the way. So all of those guys are still have to do testing. So whatever testing you have to do, and sometimes you can double dip and do them both at the same time and have the guy who's doing your procedure qualification be qualified at the same time. But all of that information for this particular code is in Article 3, welding performance qualifications. But it's just worthwhile taking the note that welders and welding operators have to be qualified in all the guidelines that exist for welding procedure qualification. There's their own separate guidelines in every single one of these codes about how you qualify the individuals themselves. Now we get into stuff that I'm sure Curtis will dwell on at some point, but the welding data itself. So this is where we talk about things that you'll probably hear in the industry at some point, F numbers and P numbers. So we're talking about the different base metal classifications and the different filler metal classifications. So P numbers are the base metals. I have this link here. It's literally a site called pnumbers.com. You can go to it and you can read all of the P numbers if you'd like to know where your base metal falls in here. But more or less, the important thing to take out of this is that all your base metal qualifications are listed here, and it tells you based on what you're testing, what you're going to be qualified for. The important thing to see here is that if you just take what you're doing for a test and apply it and say this is good enough, then you're going to be limited to what you've done there. But if you take the time to read it and make sure you're understanding where that qualification range actually gets you, you can actually do some smart things to save yourself some trouble down the road and eliminate some of these things. But you can see here, like if you're trying to weld any unassigned metal to the same unassigned metal, so something that isn't listed in any one of these P numbers, then the qualification range is only that test, right? So it's maybe not the most advantageous way to do it. And if there is a way for you to do that, then you want to take that route. Same thing exists for filamentals. So F numbers, same silly site exists, fnumbers.com. Essentially this just covers all the filamental classifications, and welders can be qualified for different ranges. The same as weld procedures can be qualified for different ranges based on where you test. So if you test, and again Curtis would know this much better than I would, but if you test at certain F numbers, you'll get a larger range than if you would if you're testing just for the one you might be using in that particular circumstance. And then the last one here is standard weld procedures. So this is the thing that I said is not super common in Alberta. This has virtually no notch toughness, well it has no notch toughness applicability, so if you're trying to do low temperature stuff, i.e. Alberta, you're not going to be using these standard weld procedures. And the silliest thing about using these at the end of the day is you still need to do the testing for them, so it doesn't even alleviate you of the need to do a weld procedure qualification. You still have to do the qualification. It's just a sort of a way to provide you with a guideline. And the other thing is you can't do any combination of these standard weld procedures. So on a weld procedure you're building yourself, you have some flexibility. You can make it applicable for many things, do the testing that's appropriate. You can't do that with these standard weld procedures. The only place that becomes relevant is structural. Which brings me to our next topic, which is structural weld procedures. So if you have questions about the first two sections, pipeline, or about the pressure cell life, you can ask me. Does anybody have any questions right now? Shoot.
So you said there are no pre-qualified WPSs?
For pipelines.
What if it's in the same service, same environment, same?
It's not, so you can use a previously qualified one if your client or whoever, the contractor allows you to. So you can use weld procedures that you've qualified beforehand, but there isn't ones in the code that, it's like a recipe, right? So in certain code books where you have pre-qualified weld procedures, you'll literally open up the code book and it'll say, okay, if you do these X number of things, follow this recipe, fill your boots, go ahead, you can start welding right away. But in most cases, so for the pipeline industry, you need to qualify that procedure. So you're allowed to use the qualified one again in a new project, but there's no existing recipes available for you. If your company qualifies them, then you can go back to your recipe book and use those ones, but you can't use new ones, if that makes sense. Does that answer the question?
So you can make your own, like use your own WPSs?
Depending on the
You
client.
won't find that
It won't be in the code. It won't tell you, here's the ones that you can use, kind of thing.
So for pipeline, what steps do you actually have to go through to qualify a procedure?
Essentially, a welding engineer, whether it works for the company or it's outside of the company, a third-party welding engineer, will go through, be told, we're going to weld on X80 pipe with, we want to do this with flux core. And that welding engineer will sit down, design the procedure, look at the code, find out what he needs to do for testing in order to qualify the procedure, go through all these different things in terms of testing, get the testing, do whatever NDE or DE that's needed. And then once all of that is completed, the engineer will come back and say, okay, we did the test met all the stipulations of the code. I'm now going to stamp this weld procedure. I'm going to say this recipe is good to go out of the shop. And then it's not done there, then he has to go and hand it over to a project manager who hands it to a client or to the governing body, and the governing body will then look at it and say, whether it's a client or whoever it is, will look at it and say, yes, this meets the requirements, we agree, go ahead and use it. Some of them put their own stamp on it, some of them will just review it, and you only know if you're good whether or not they say you're good. So that's the process, is a welding engineer somewhere along the line, or somebody who's being called a welding engineer, will go through, design all of that, do the testing, all those things, and then at the end of the day, get it back. And it'll either be approved by the engineer or not. The engineer at the end of the day is taking the onus on them. They're taking the responsibility for that procedure. Just the same as any engineer, like a civil engineer would go out, design a building. The same thing is true for the welding procedure and the welding engineer. The welding engineer is taking responsibility for that welding procedure. Sometimes it's a third party that will look at it, like APSA would look at it, or a client, but that process is all the same.
One comment on pipeline welding procedures, because there's a lot of questions about it. There's kind of a trend now as people move towards automated pipeline welding, where you wouldn't actually want to reuse an old procedure, because if you qualify on exactly the same pipe you're using with exactly the same heated wire you're using, you can actually define your own acceptance criteria. You can say, we understand this material and this wire so well, we are going to define exactly how large of a flaw we can have before we have to reject the weld. And you can only do that if you use exactly the same heated material that your pipe is and exactly the same heated wire. And a lot of people, if you're building a large pipe and you're automating it, it's in your best interest to have those kind of self-defined acceptance criteria. So you wouldn't want to reuse an old procedure. And that's called an engineering critical assessment. It's still not used all the time, but a lot of times if you're doing automated welding, you're already kind of invested in the equipment where it's reliable enough that you know as long as you use the same material and the same wire, you will reliably produce the same weld every time.
And certain codes will allow that, and that's something where a client would allow that kind of work. Now we get into the enforcement side of life, it's the structural. And whatever you thought was not regulated before, you get all the regulation you could want and more in the structural world. So in Canada Welding, CSA W47-1 is more or less the certification Bible, and that's administered by the CWB, or the Canadian Welding Bureau. And the Canadian Welding Bureau, unlike a lot of different ones, completely administers and adjudicates this code. So that means that when you build a weld procedure, your only yes/no is the Canadian Welding Bureau. You submit that, you've done it, they'll tell you what testing to do, everything happens that way. But you can get yourself into some troubles that way because, well, the reality is there's two things. One is there's humans on the other end of that line. It's not a perfect automation. So sometimes they don't consider your best needs. They're just considering, they're doing their job, right? So if you tell them, we want to do this, and you don't tell them anything else, they're going to say, okay, great, go do this. But it might not actually be what you need to know. So it's worthwhile taking into consideration that a lot of companies that actually operate in the structural world, even though technically they could get away without it, take a lot of the onus on themselves and employ welding engineers to get around this. So everybody involved in an operation in terms of welding needs to get certified through this standard. So engineers have to be certified, welding supervisors, welders, welding operators, even tack welders. So even the guy who's literally just taking two plates, putting them together, and just putting two little tacks on it, needs to be certified by the CWB. Some people might call that a money grab, but I mean, we're not going to put labels on it. And they, like I kind of mentioned before, they define a different definition for WPS. So what you've heard for WPS before is your recipe. Here they define two different things. They define WPS, which is welding procedure specifications. These are process-wide recipe books, essentially saying if I'm going to weld with stick or I'm going to weld with sub-arc, this is how I'm going to do it. I'm going to obey these certain rules, and you have to submit that to CWB to be certified. And then they have the actual welding procedure data sheets which are the individual recipes. How am I going to do this weld? And all that needs to be certified. 247-1. 3 different levels within W47-1 that you'll hear of is Division 1 companies. This is an important one for you depending on where you go to work if you ever plan on working in the welding industry. Division 1 companies employ a welding engineer full-time. So Supreme Steel, there's myself, but I'm a welding engineer in training. I'm not a PNG yet. And we employ one more welding engineer. So there's 2 of us for one company, which is more than some other companies even have consideration for. Then you have Division 2, which means that you keep a retained welding engineer. And this is a really, really good gig to get into if you're a welding engineer, because you can have like 16 companies on retainer at once. And it just depends on when they come to you asking for your services. But you essentially act as their employee for the time that you're being asked to. So if they come in and they say, okay, we need Joe to come in, Joe the retained welding engineer, and Joe needs to build these X number of procedures for us, that's what he's being employed by them and is essentially considered a full-time on that way. Some of these welding engineers have a really good gig and they get paid a part-time fee no matter what, but that's fairly rare. You're normally paid for your services rendered. And then you have Division 3, which is that they're not required to employ or retain a welding engineer. And this means that they're literally just giving the procedures to the CWB, and the CWB is essentially doing all of the work for them. They're charging them for it, and they're charging them quite a bit more for it because they have to go through and design the procedures, but they're under no requirement to do it themselves or to even contract somebody who does it. The 3 different levels are important because it allows you to get different work. If you plan on building a bridge or a building in Canada, you will not get that project if you're not a Division 1 company unless you employ those people in-house. Just flat out, you won't get the work. It's almost a requirement of every single specification. It says in the first line, contractors shall be certified as a CWB W47-1 Division 1 company. So all of those requirements are laid out in the industry, and so oftentimes people have motivation to seek the higher level of standing here. So welding procedure specification, I kind of already went over this, but these are essentially, they're supposed to exist for primarily by the use of the shop personnel. I don't think I've ever seen a shop personnel of mine open up a weld procedure specification. So these govern a process individually. And essentially what this will state is what you should be doing within that process. So for stick, for instance, it would go through and say, all right, we should be welding only in this kind of either DCEP or DCEN. It would say which ones you're allowed to weld in, and all of your welding procedures should adhere to that welding procedure specification. I will tell you that weld procedure specifications have to be submitted by the individual process, but very often, even though clients will ask for them, and the CWB will review them, this is not a super useful document. This document is one that gets created, it sits on a shelf and nobody really cracks it. Somebody like myself will really care about this document because it is where I can put all of my information, but nobody else really cares about this document. And in fact, for our company, one of the first things that I did is I created a new weld procedure specification because I saw what they were being used for and what they actually were. And instead of building them for one process, I built them for all processes. And I made it into one document. So I have this like Goliath 90-something page document that just covers all weld procedures, all different welding processes in one document. And that way when we're referring to this, which you have to refer to a specification on each one of your data sheets, we refer to one document. It was just a little bit easier for us, and that way I could list all of the relevant codes in one document. Now we get into the data sheets. These are the actual weld procedure specifications we saw before. So these are for the welders and the welding supervisors on the shop floor. These tell them exactly what they need to do. Same sort of information we talked about in Z662 is all there. Parameters, the joint prep that you need, the process that you're using, all of those things are in there. And actually the CWB has one really good thing in there, which is that they have this welding procedure guide. And they go through and they give you a sample welding procedure, how you should build it, and they go through each one of the little boxes in there and they tell you exactly how that breaks down and how you can build your own weld procedure. So they do have that information out there for people to learn from. And then these are all going to be very, very specific, so the recipe is still tied to the same things that were in the other codes. It's specific to the process that you're using. Now, the line at the bottom here is the one that I was talking about before, where you need to have your weld procedure data sheet actually conform to your weld procedure specification, which is sort of a relative term because nobody really looks. So both of these codes are administered by the CWB, 47.1 covering the certification, and then W59 actually covering how you actually go about and weld these. It has all of the pre-qualified joints. Pre-qualified joints are an extremely prevalent thing in the structural industry. Alberta's a little bit of a weird case because we do so many things that need low temperature requirements, but many of the joints that you'll see in just standard building construction are pre-qualified joints. So a fillet weld, if I want to go and do a fillet weld, I need to have a procedure, I need to submit that procedure to the CWB, but I don't need to do any testing. If there's no low temperature requirement, I just need to submit that procedure. As soon as I get it back stamped, I'm good to go. I'm off to the races. So the same thing is true, AWS D11, and actually, I'm sure that the CWB and the CSA codes wouldn't like to admit this, but pretty much everything that they have is lifted from D11. They stole all of it. To their credit, they did make some of it better in the long run, but pretty much everything is stolen. Welding symbols are stolen, joint preps are all stolen, welding parameters are all stolen. It's all stolen from D11. This is the American code. And they have improved it, but, you know, it does come from the same place. Which is useful because then when you go to actually qualify things, you can sometimes dual qualify for the states and Canada at the same time. You can't use one of these codes without the other, they require each other essentially. Welding symbols, I know you guys have gone into painful detail on welding symbols in the past, so I won't go through that, but all of that conforms to the American code just as much as it conforms to the Canadian one. One of the interesting things about W59, so this is sort of the design and application code, is it covers both statically loaded and dynamically loaded structures. So statically loaded, we're talking like office building. It's sitting there, it's undergoing pretty much the same loading the entire time, it's a dead loading, it's not doing much. Dynamically loaded structures would be something that's maybe undergoing wind loading or something like a bridge, right? They're driving over a bridge continuously, that would be considered dynamically loaded structure. All the materials that are considered by the code, it essentially covers essentially 95+% of the materials used in steel construction. In the first three groups of it, it does have more groups in it above and beyond that, but every group past 1, 2, and 3, like all the ones up above that, are all very, very high strength steels. So typically, when you're building a building, you're not going to build it out of like, I don't know, 700 QT steel, because your building is going to break, it's going to be too brittle. So a lot of the steels that are in here are very, very ductile or maybe lower strength materials, but it covers essentially most of the structural industry all in one set there. So very often when you'll see it on the example that we go through for the weld procedure data sheet, is those three groups are all considered as one group within the code. Now, one of the things really interesting to note here is that, well, they have a whole bunch of pre-qualified joints. Pre-qualification for notch toughness is not given. So that means that if you want to weld at low temperature or you want your material to be good at low temperature, you need to test for it. They're not going to give you pre-qualification for that. And that's often the case that we run into. We're 99% pre-qualified, except where we have low temperature. Now, unfortunately, like 75% of our work is low temperature. We pretty much always have to do procedure testing. But you can be smart about it and save yourself a lot of time as you go through it. Welding symbols, like I said, I'm not going to dwell on this. It's in here, but you guys have gone through that in more detail than probably you want to repeat. And then in here, I just want to take this one snapshot out. This is from the CSA W47-1, and this is just for welding positions. So I don't know how much you guys have looked at welding positions before, maybe? Not at all?
Positions?
Yeah.
They know them.
Excellent. And if you guys know your positions then, this is just the highlight from the code. One of the things that's interesting to note though, and I will point out, is that these positions should be rigid, but they aren't rigid. And in the code, they actually give you limits on these positions. So you can be horizontal at like 15 degrees past horizontal, right? So there's limitations on these that are actually placed in the code. And people play tricks with this. So if you want to qualify a horizontal weld, but you don't think you can actually pass the horizontal weld in the horizontal, you can tip it a little bit in your favor to make it a little bit easier, and you're still within the code regulations. So those are always things important just to watch out for. You can use these in your favor, but you don't want to play too many games outside of the regulations of the code, because people will catch it and will call you on it. And then also up here just kind of highlights what you're testing for. So if you test in the overhead position, so these are the different welding positions here, and based on where you tested it on, so for a complete joint penetration groove weld, if you test in the overhead position, you'll get credit for the flat position and the overhead position. And pretty much all of them, you can see the trend. Doesn't matter what position you test in, you get credit for the flat. So if you need a flat weld procedure, it's pretty dumb to just test in the flat position, because no matter what you do, you're going to get another position out of it. So it's worth your while, provided you can pass it. I'm not suggesting anybody do overhead sub-arc, it's not going to work. But if it's worth your while to qualify in a different position just to get that extra qualification out of it.
Then what's the difference between flat and one then?
No difference.
Because you have positions.
So the welding position, 1G is still flat, right? But it just means saying that you get flat for all of them.
Okay. Okay, so if you do 2G, you pass 1G. That's essentially what it says. Okay.
But all of them are more or less, you do any position, you pass 1G or 1F or whatever.
But they call it flat.
They call it, I don't know why.
Okay.
On your weld procedures, you'll see it in the example that I showed, we actually list like 1F, 2F, and then we'll say flat and horizontal as well. So we say both. I don't know why. I don't have a good answer. Probably because people looking on the floor might not recognize what 1F means, right? Which, troubling or not, is the case. So the last thing I wanted to do here, and I think I left myself enough time to go through this in detail, is to actually go through a case study. So I have a weld procedure from our company that I've scrubbed down, and actually I'll give Patricia to give you guys. And
I'll upload it. We don't have we have the old notes uploaded, but we will upload these new ones from
Yeah.
Aaron and Curtis too. We can upload yours later?
Yeah, I just need to trim some stuff out.
Yes.
And then I have a weld procedure that goes along with this example. So we're gonna do an example here. We're gonna look at how we actually built a weld procedure and go through it in detail. So this example is one of the ones that's very, very common for us that causes headaches along the way, but the example is bridge construction. So doing a flange to web fillet weld. So you guys know what a bridge girder looks like in general?
No.
No?
You have to say it briefly.
So if you guys have seen what an I-beam looks like, is in a beam where you have one big plate, plate in the middle, and then another big plate in the bottom. So that's what bridge girders look like. The top plates and the bottom plates are both known as flanges, and these are very, very thick plates. So for a bridge girder building in Alberta, you could be anywhere from our example here where I said we have 40 mil thick plate. You could be anywhere from that all the way up to 100 mil thick plate, so 4-inch thick steel. And we're talking 4-inch thick steel, and it could be 400 millimeters wide, so we're talking huge, huge pieces of plate, several feet wide. And these plates are, in general, for this kind of bridge, would be about 60 feet long. So these flange plates are massive, and then you have your web material. And the web material spans from anywhere from 2 meters, so this is the plate that goes in between the two flange plates, that's your web. And that web material can be 2 meters big. We're actually bidding a project right now in Vancouver. The size of it even blew me away. It's 7 meters depth. It's insane, absolutely massive. It's so big that we can't drive on the roads. So we had to break the design into 2 girders stacked one on top of each other, because you can't fabricate a 7-meter deep girder and expect it through on the road. So absolutely insane the scale that we deal with. But essentially, the example that I want to use is just a bridge construction where you're talking about the flange to web fillet weld. So this web sits on top of the flange, and then you fillet weld on either side of that. And you guys, I'm guessing, know what a fillet weld looks like? Triangle weld in the corner in between 2 plates.
Yeah, but probably you have like 100 passes or something.
Actually, you really want to scare yourself? Most of these welds are done in an 8 mil weld, single pass. One shot, boom.
7 meters.
What's that?
7 meters is for it.
8 mil weld. It's strong enough, don't worry about it. So the material that we use for this particular project is 350 AT, so 350. This is one of the biggest lines you'll ever see in industry. 350 is supposed to be the yield strength of the material. It's actually not. Somebody did a conversion somewhere back in the day, and you have this whole difference between the 50 KSI and the 350, and it's supposed to be completely across the board. It's not. So 350 materials, yield strength is not 350, it's 345. Because of a conversion difference, but somebody decided they wanted to call it 350, and then somebody else, like 5 years ago, got really confused and said that's dumb. And so now you see new grades of steel coming out, and they're being called 345W and those kind of things. It's a whole mess. But they essentially made a conversion between the imperial and the metric and decided to call it 350. So 350 AT. So all that the A stands for is atmospheric. So that means that this, if you drive under bridges in Alberta, you'll see that they look orangey or a little bit rusty. Don't fear, they're designed to look that way. They're designed to rust. Rust is a bad term. They're designed to have a patina. That's the fancy term that people say to make you feel better about it. So patina is essentially controlled rust. So it means that your steel is going to rust no matter what, but it's going to rust to a very specific level, and then it's going to stop rusting. And no amount of corrosion is ever going to hit it. So these are designed, they essentially have added nickel in the steel in order to get that property out of them. And then the T stands for essentially the toughness requirement. So that's our low temperature requirement. So Cat 3 is a requirement that is enforced in bridges in Alberta. And that Cat 3 essentially means what I said before, which is 27 joules at minus 30. That's what your base material, your filament metal, and your weld all need to be able to provide, and your heat effector zone all need to be able to provide in order for you to pass this test. And it'll all be hit with a Sharpie impactor to test that. Basically, you buy it from a mill and it's already been tested. So we're doing this in the horizontal position for a fillet weld. So as in, you're going to have web standing up like this, fillet, your flange underneath, and you're going to run your subarc, which is the process that we're using here. We'll get into that in a second, but we're going to run our weld in that joint at sort of a 45-degree angle in that weld to produce a fillet weld all the way along there. I note this because this does happen in Alberta, but we're not going to do this for D15 compliance. D15 is the American Bridge Welding Code. As I noted, almost every single bridge in Alberta has to be to D15, but we play some really weird game where you know how things get confused between metric and imperial? Imagine 10 times more confusing when you go to mixing codes. Essentially, what the Alberta powers that be have decided, so Alberta Transportation have decided, is that all bridges in Alberta need to be compliant to D15, as in you need to fabricate, you need to preheat, you need to have all your tolerances to D15, but your weld procedures don't need to be to D15. So your weld procedures are still done to the Canadian code. So that's why we're using this example. For whatever sense that makes, that's the way that they choose to do it, and it's the way they choose to separate it. So essentially, everything we do in terms of our shop will all meet the requirements of the D15 code, but all of our weld procedures are not qualified to. In this example, I've just selected a 40 mil flange material and a 14 mil web material. 14 mil is a little smaller than you typically would see, but I'm doing it for a specific reason, to illustrate something in the code. Typically, you'd be somewhere in like the 19 mil to 1 inch range. Speaking of mixing measuring material, you have to live with it. That's the way the construction industry operates. So if we go through, we're going to set up. We know we have to do testing for this because we are doing, even though the fillet weld is a pre-qualified joint, we're doing low temperature. We know we have to do testing. So we're going to go through the process of actually building this PQR, and then we'll get to see the end result of the weld procedure data sheet at the end of the day. So start off with process. So for process, we're going to go with the sub-arc process. Now the reason for using sub-arc is a couple different reasons, but essentially it's code stipulated. Every single specification on how to build a bridge will say your flange to web fillet welds, so the most critical weld in your structure, must be done with sub-arc. Absolute must. The reason for that is that it's very consistent. You don't get a lot of issues with sub-arc welds, and it's also very, very efficient. Now, obviously, the code doesn't care about efficiencies, the fabricators do, but the sub-arc weld is very, very consistent. And it's consistent to the point where actually, there's a clause within W59, the construction code, that says that when you weld with sub-arc, you get to add essentially 1 weld size to your weld. So if it makes you feel better about the 8 mil fillet weld, it's actually a 10 mil fillet weld. So they consider, because of how deep the penetration characteristic is, that you're actually getting a 10 mil weld, even though all that's on the outside is 8 mils, right? Because you're penetrating down, and those 2 millimeters in the corner there are adding to the strength of that weld. So we go with sub-arc. Project specification requires it, but also it's good for us because it allows us to downsize welds. The maximum size of a weld you can do by code in Canadian construction codes is 8 mils in a single pass. So typically designers will design for 10 mils, and then you get to downsize it to 8 because you're stipulated to use sub. So then your test coupon. Your test coupon, you're going to go and you open up the code, you're going to say, okay, I would like to qualify the notch toughness requirement of a fillet weld. Well, Sharpie testing a fillet weld would be pretty nonsensical. You wouldn't get a result that made any sense because how the heck would you put a Sharpie? If you see the Sharpie sample, they're essentially these 10 mil by 10 mil blocks that are about 55 millimeters long. How are you going to cut it out of a T-section, right? It's not going to work. So you test it on a groove weld with the same parameters and you get to that same result. So even though they're pre-qualified, you need to actually go through and do the testing because of this notch toughness requirement. Some of the fillet welds, depending if you're doing them in a weird position, you might have to do a macro edge specimen, but very often you don't have to do that. Now these specimens, because I said the C2B is very, very involved, are all specified in the code. So now we're going to look at the plate, and the minimum requirements for the plate, you need a 300 mil long plate. Your thickness is going to, we're going to go over that in a second, but essentially you need to produce a groove weld, and then you can see exactly where you need to extract these things. So you can see where your weld joint is, and you can see where it's supposed to be hit by the actual CVN test. So where the hammer will actually, where the knots will be placed, it shows you exactly where you need to do these sample extractions. And you can see the tension testing. We don't need to do that. We're doing a fillet weld. Our joint's already qualified. We don't need to worry about that. All these hardness things, we don't need to worry about that either. Our joint is already good to go, but we have to make sure that we're passing our CVNs. So it tells you exactly what kind of plate you have. It also tells you to do a 300 millimeter long plate, but that's a minimum. Typically, we'll do something more along the lines of like 400 millimeters. So instead of doing a 12-inch or 1 foot plate, we'll do a 16-inch plate. The reason for that isn't great, but it's because if you fail, one of the great things about welding is failing a test doesn't really mean failing a test. Failing a test means, well, you failed that test, sure, but you could always move over and try again. So you have that option available to us. So we build our test plates long, on purpose, just to build into that, have that kind of second go around at it. The C2B has started cracking down on that a little bit, but people in the industry try to abuse that as much as they can. Filler metal. because this is a weathering steel, and it's nickel containing in the actual steel, you need to use a nickel containing wire. And so when you actually go into the code, W59 will tell you, based on this table here, it will tell you, because of dynamic load structure, you need to have a minimum of a 49 tensile strength, 49 KSI, not converted over because again we work in both units. You need to have that minimum strength of your wire and flux combination. But in reality, we actually tend to use a higher strength, and the designers like this. We tend to use a little bit of an overmatch for the base material strength, and we tend to use this sort of 55 KSI wire. And we also need a nickel containing wire because we need to make sure that our weld rusts as well. Because if your weld doesn't rust by itself, because it has nickel in it, it's going to rust and then it's going to fail because that rust isn't going to stop. One of the things to know here is that I specified neutral flux. One of the things that when I got into our company that we had was we used an active flux. So that means that your flux is actually doing some of the alloying. So in subarc, you guys know enough about fluxes, I'm sure. But your flux with an active flux is actually doing some of the alloying. But what that means is that by the CWB stipulations, if you change the electrode size, any change is considered a change of essential variable. So that means you qualify one wire size, and you want to use any other wire size, you've got to redo the test. But the stipulation of that is that only applies if using an alloy flux. So if you use a neutral flux, rightly or wrongly, and I'm not saying it makes a lot of sense, but I could do it with a 3.2 millimeter electrode, and now I can use whatever wire size I want so long as it's a well-recognized size by the industry. So we moved away from an active flux on purpose so that we could go to a neutral flux and give ourselves some flexibility there. So we have our filler metal worked out now. The PQR material, that's fairly straightforward. We're doing it in a Cat 3 material. We're going to use a Cat 3 material for the PQR. Now you might think and look and say, why not do Cat 4? Cat 4 is the exact same impact energy. The temperature's just lower. So if you did Cat 4, why wouldn't you just do a Cat 4 test and then you're good, right? You passed it. Well, CWB likes their money. And not for any logical reason, because I can't honestly think of a personal logical reason, but they've said it changed from base material tested to base material with a lower mechanical property is a change of essential variable for CVN testing. So whatever sense it makes, even though the impact energy is the same, and I don't know of a single steel material, maybe you do, of steel material that has worse impact properties at higher temperature. I've never heard of it, but the CWB requires you to do a retest, which in my mind is the one true example of a money grab you can see in the code, because I can't think of any logical materials reason out there in order for this to be the case. And what's even stupider, this is a little thing that's been a personal annoyance of mine the last little bit, is that if you test a Cat 4 material, and you go back and you test a Cat 1 material, so that's passing 27 joules at 0 degrees C, now you get all of them. Now you've proved you can do it at a high temperature, and you prove you can do it at a low temperature. For whatever sense that makes, that's the way that they do it, but it's completely under money grab in my opinion. I'm bitter about it. So we have our material picked out. Now, while I've said this, we do sometimes qualify procedures to Cat 4, and then we go to the engineer of record. All these codes have these nice little clauses in there that say a reasonable engineer may make a judgment call outside of this code. And essentially it's not that exact wording, but essentially what it means is that a reasonable engineer can look and be like, oh, impact properties don't get worse at higher temperatures, I'm going to allow that to be the case. So a lot of our procedures we actually qualify to a Cat 4, and an engineer of record will allow us to use that on a Cat 3 plate. Plate thickness, this is where I included the 14 mil in there. Essentially, you plate thickness for these tests, you look, this is what you're testing on. So if you test on a plate 25 mil and over, you get from 5 mil to unlimited. Which sounds awesome, right? You do one test and you're good to go. You get 5 millimeters, which is tiny, you never build a bridge of 5 mil thick, to unlimited thicknesses. Sounds great. But then they put this nice little thing in there in the actual annex that talks about CVN testing, and it says essentially you're limited by what the sizes are. So you don't get all of those tests. What they do is they essentially eliminate it from 16 to unlimited. So if you do a 25 mil test, so our plates are 14 mil and 40 mil in this example. You do a test on 25 mil, under this it would cover all of it, but under this stipulation, you only get from 16 mil to unlimited. So you wouldn't be good for your web plate, right? So what you have to do is you have to go back, and then it says that for any of your thicknesses that you use, you essentially get that thickness and then up to double that thickness. So what we would do in this particular case is we would test on an 8 mil plate and then a 25 mil plate. So this 25 mil plate is going to cover the thickness ranges of 16 to unlimited. This 8 mil plate is going to cover 8 to 16 mil. And you have to play games like that. If you want to qualify a weld from 3 millimeters all the way up to 25 millimeters, all the way up to unlimited, what you essentially have to do is you have to go and you have to test at 6 millimeters, because if you go back up the slide, they actually say if you test it less than or equal to 6, the minimum thickness is half of the thickness. So if you want to test from, you want to be good from 3 to unlimited, you have to test at 6 millimeters, you have to test at like 10 millimeters, and then, you have to test at 10 because you get 12, or you can test at 12, one of the two. So the 3 millimeters will get you 3 to 12, then you have to test at, let's say 10, which gets you 10 to 20, then you test at 25, which gets you 16 to unlimited. A lot of testing, a lot of money. American code, that's one test. The D15 test, this is where I said the Canadians got a little bit past them. This 25 mil plate gets you 5 millimeters to unlimited, just like the original version of the Canadian code. It just came in because they essentially have made this argument that for smaller plates, it doesn't distribute the heat in the same way, and so you can't make that same prediction. Rightly or wrongly, that's what they've said. Welding parameter targets, that's going to be dependent on your PQR. You can do a lot of the things and learn a lot of the things from Patricio's class, and you can determine those parameters in advance or try to predict those. But that's going to be resulting in your PQR. Your PQR, the parameters that you do there, are going to limit what your parameters are on your actual WPDS. And then preheat is determined by the code. So in actual practice, we would have to follow the D15 preheat for this particular example, but the one that would be stipulated in our weld procedure is this one from W59. It just stipulates based on the thickness of material what your preheat is going to be. So if you're welding 20 mil thick, I think the thickness ranges are 0 to 20 mils, 20 mils to 40 mils, 40 mils to 60 mils, and 60 mils and above. And based on whatever range you're in and what material class you're in, so higher strength materials will force you over a little bit, but your preheat will be determined on that. And some of the preheats are literally nothing. Like it says 10 degrees C. Well, you're never going to be welding in a shop that isn't 10 degrees C, so you don't have to worry about that. Go in the field, that's a different story. But we're not welding
One
bridges
quick
in the field.
thing. So thicker plate require preheat, right?
Yes.
Do you guys know why? Why thicker plate would require preheat?
To lower the cooling rate?
That's one theory.
Because there's more of it, so it absorbs more of the heat that you're putting in.
Yeah, similar, right? Like if you look at the formulas for cooling rate that you guys have, when you calculate for like the 2D cooling, the thicker the plate, the faster you cool down. And if you cool down fast, as you know from metallurgy, right? You can get these hardened structures. And because there's always hydrogen around, you can get hydrogen cracking or not pass the code. You don't need to specify hardness, right? In this code. But in yours, yes, right?
It depends.
It depends, right? But so sometimes you're gonna have a cracking. Sometimes if people care about hardness, that's a problem. So it's super interesting. So you guys take this class, and you have to endure all these questions about heat transfer and all that, and then you listen to him. He represents the real world, right? And sometimes, if you're lucky enough to be an engineer of record or a big, highly paid consultant, is that knowledge the one that buys you an edge when you have to make arguments? And you have to use our formulas in your case
I've
too.
used the formulas used in this class way too many times to explain things to people who are of questionable intelligence. It's just my politically correct way of saying that to deal with some people I don't like. In this particular case study, so because all of this resolves around low temperature requirements, so we need to do CVN testing. So this is the Sharpie that you will have seen in some of your materials courses. If you haven't, there you have a picture of it. But essentially all of this testing, so all of the PQR testing, all the welding will need to be done in the presence of a CWB representative, which you have to pay driving time to because again, money grab. But essentially all of this will then need to be tested in an accredited lab, which again is only the ones approved by the CWB. So it's all working within its own system. The nice thing about this is that you have very, very accurate, like people complain about the money, and even I complain about the money aspect of it and the sort of bureaucracy aspect. I submit a welding procedure and I might not get that welding procedure back, done and ready to go in my particular industry for 3 months, which is absolutely ridiculous. It seems very, very painful, but the good side of it, if there is a good side of it, is that it is all very controlled and regulated. You don't find a lot of people who are working outside of code in this industry. When you go to the States, and I have a slide on this in just a second, when you go to the States, it's cowboy world. Everybody just regulates their own welding procedures. So you go to a company and they may be like, yeah, we nailed it, we have all these welding procedures, we're good. And then you look at what they're doing, and you're like, what was this guy on? Like, sometimes it doesn't make sense, but no, there's no governing body, it's just clients. So again, if I submit my work as an AWS certified company to a client, and the client has a civil engineer, he's gonna look at the document and be like, looks great, man, here you go. It doesn't mean that it's right, right? And so that's kind of the problem that you run into, particularly in some of the other sides of the industry. So as much as people like to complain about the CWB, and everybody likes to complain about the CWB, they are doing some good service in terms of making sure it's actually regulated. Some of the easiest jobs we've ever done are doing jobs in the States, where we're essentially just qualify our own welders. Even welder qualification testing, this is a terrifying one, but welder qualification testing in Canada, all that's regulated. So if you have a guy who goes and does this test, he fails it, he gets one more chance. If he fails that again, he's got to go and do training. In the States, it's literally like, here's these 25 samples, Jimmy, I hope you pass one of them. Doesn't mean that he knows how to do that process, it means he might have gotten lucky once, right? So there's trade-offs to both sides of this. So at the end of the day, what is our WPDS qualified for? It's going to be a submerged arc weld procedure. It's good for group 1, 2, 3, so just the basic materials with no CAT requirement, because we essentially are double dipping on our weld procedure. We're saying we're going to use this because it would be a pre-qualified joint, which is to fill it. So where this material isn't involved, it's just a pre-qualified weld procedure. Where this material is involved, we've done all this testing, we've shown that we can do this test from the thicknesses of 8 mil to unlimited, qualifies what we need to do in terms of the 14 and the 40. And because we've done this testing for the CVN, one of the nice things is this isn't just limited to the fillet weld. So one of the reasons that we tested, we made sure to go down to 8 millimeters, is now we can take this and I want to do a V-groove. I'm good, I just need to go get the pre-qualified joint number, I need to refer to this PQR, and I'm good to go. I'm off to the races. So that's what I'm talking about in terms of planning that out. You can take a lot of time to plan that out, and if you do take your time up front, you can actually make sure that you have no issues going forward and you never be called out, and actually you can use this going forward into eternity until they update the code and then it's no longer valid, which happens like once every 5 years. So you get a good 5 years of luck, and then he runs out. It gets to the point where our company in particular, granted we have a lot of history, we have something like 3,000 weld procedures on record. We use like 200, we have like 3,000 on record. Now a lot of that is because we grew by purchasing companies, so we've got all of their history too, but there's some different things in there. And the one thing I wanted to highlight here is there's a new requirement, this is new as of this year, this new W47-1 got released. This wouldn't affect the weld procedure that we have now, but you would actually have to do an additional test to show that your single pass weld can pass the requirement. So on your 8 mil test, where you build that 8 mil test plate, you try to do that if possible in one single pass. Because that would say that when you do a single pass weld that isn't affected by any other passes, that one pass, that those parameters can pass the test. So for a single pass fillet, you need to do a single pass weld. If you don't do that test, guess what? Even though you can do an 8 mil pass in one 8 mil weld, in one pass, you're not allowed to unless you do that test now. So just another added level in there. And the parameters that you use on your PQR will give you some sort of flexibility. The only thing you're really limited by is the upper end of the heat input for notch toughness. So notch toughness, in particular for low temperature applications, whatever your heat input is at a maximum in your testing, that's where you're limited to. Besides that, you can use pretty much any, within reason. If you go to do a stick procedure and you say you're going to use 5 rep amps, people are going to look at you and be like, no, you're not allowed to do that. But you get some flexibility in terms of the parameters there. So. And then I've already gone on enough about the AWS. So what I wanted to do here before I sign off is I actually brought in the weld procedure that was qualified using this testing. And this is sort of a standard sheet for our company. I've made it nice and CCWJ for you guys.
Wow. It's a keeper.
This is fairly reminiscent of what you'll see in industry. Some data sheets have more or less information. There's the guide that's provided by the CWB, and they'll provide you with the standard one if you want. We've done this for our own company because we like to manage it inside. But you can see that all the things that we talked about in here are still relevant, right? So you have the reference standards. So here I've referred this to W47-1, W59. The AWS D11, we can kind of ignore that. It's just because we wanted to have our data sheet as a pre-qualified joint anyway, so we wanted to have it applicable to more codes. So we put a stipulation, because the D11 testing is different for notch toughness. So those little stars you'll see below, I have a special remark in the bottom that says you can't use this for notch toughness. So here's our joint, it's a fillet weld, right? So you have, this is your fillet weld, this is your web material, this is your flange material, and the thickness ranges of these two things, so you can see T1, T2, these are your two-part numbers. Here's the applicable steels that are allowed to be, so this is that group 1, 2, 3 that I was talking about, of those two tables. So we said, essentially this is good as a pre-qualified fillet weld joint for both these tables, so dynamic and static, static and dynamic loading. All those material groups, so the basic material groups, and now we get into the specifics. So we have 350 AT Cat 345. So this was actually qualified in advance of the whole Cat 3, Cat 4 thing. So you can ignore that, but essentially it should just say Cat 3. And then this is our thickness range. So you can see the thickness range for both of them, because we're using the same PQR, is 8 milliliters to unlimited, and here's our special requirement. So because this was done to a Cat 3 level, or sorry, Cat 4 level in this particular case, this is what I was saying, where it's a little bit different than what it was before, but we did this, and that's the special requirement. So here it should actually say minus 30 degrees, but this is the case. Then it says what the joint type is, so the joint types you guys would have seen, so T-lap corner, oh that's not good. I think that typo's been fixed in the new version. So penetration, it's just a fillet weld, so we're not doing anything crazy. If this was a CJP, it would say complete joint penetration, or partial if it was a PJP. And then here you would have like single groove weld or whatever it was. ETT, not important for fillet weld, so that's your effective throat, not important. I have some stuff at the back end of this presentation, which I included just for completeness, so you guys have some of these definitions in there. Whether you need to use a back material, all those things, whether you need to back gouge. So for welds where you're welding from one side, flipping it over, you don't just get to flip it over and go to town. You sometimes need to back out, so you need to use a carbon arc gouger and gouge it out and weld in there. Number of electrodes, so this applies for sub-arc, so you can have 2 wires inside a sub-arc cup. Here we're not using that, we're just using a single one. Has the electrode space and those kind of things. Electrode extension, which you guys will have gone over, you have to specify that. You only get what you tested for.
What do you define as electrode extension? The contact tip to the plate?
Yeah.
Okay.
Yeah.
So it's not what we call it.
It's not the same.
But just to be aware that the same words
Don't mean the
different
same.
things. Yeah.
Nozzle diameters in there. And here, technique, that's where you note things like stringer beads. And if you try to say, if you did a PQR with a stringer bead and then you try to put a weave on here, they'll deny it. Particularly for these. And then here, you'll see that pre-qualified joint number, because it's fillet weld, it's not applicable. It's not actually in a pre-qualified joint table. And then the procedure test qualification, so if you scroll down now, it says C note. So if you go down here, I've removed PQR numbers, because those are our PQR numbers, I wouldn't do you any good anyway. But essentially, it would refer to what the PQR numbers you need to see there are. So that the CWB has all of those things on record, it's their numbers that they're generating, so it would refer to them there. And you can see what I was talking about for the D11. It says only ASIM specified listed in AWS D11 are pre-qualified for D11. Additionally now, because the AWS D11 notch toughness requirements are different, we would need to have a note in here, and our new version of this procedure does, where it has a note in there that says, these results are not good for CVN toughness, for CVN requirements for D11. Essentially stating that this is limited only CVNs to the Canadian code, has the interpass temperature in there is a maximum interpass, and then has the preheat in there as well. There's no post-heat weld heat treatment. Very rarely you'll see any post-weld heat treatment on a structural job in general. Not the case in Curtis's world. Post-weld heat treatments are used all the time. Structural world, we try to deny it as much as possible. I know people don't like structural heating, and it takes a lot of time. And in here you can see what we've qualified in terms of welding wire sizes, so 2.4 millimeter. I have the imperial in there because we can speak both languages. Technically all we're required to have is the metric, but we put both in there because the guy on the floor, if you tell him to use a 2.4 millimeter wire, is going to tell you to go do something. And then here we have pass layers and all that, but all these would be single passes. We have wire feed speed noted, current, polarity, voltage, travel speed, and then you're required, because we're using a CVN, you're required to list your heat input. And that's listed in kilojoules per millimeter. Very oftentimes in industry, people talk in kilojoules per inch. You kind of have to get used to making that conversion naturally. But this 3.3 would have been the maximum heat input of the PQR. So you wouldn't be able to exceed that in any way, shape, or form. And actually, you'll note that our parameters, I don't actually know, so don't, if I'm wrong, check me on it. But this new version of the procedure, I'm sure it's true, I don't know about this version, but no combination of these parameters, by doing the heat input calculation, should you be able to exceed these through this 3.3. It shouldn't be listed on there. So you are allowed some sort of a range of parameter variation, but in no way, when you're using CVN properties, should you be able to exceed that number. So yeah, that's the data sheet. So that example essentially conforms to that data sheet. There are some minor differences. If you remind me, I will send you an updated version. The only other thing is that I've included in here is I've included some of these things about groove welds and different parts of the weld, which I'm sure you guys are more than familiar with because Patricia has probably taught you that in excessive detail. But I have it all included in here just in case you guys find it relevant. So besides that, that's it.
Thank you, yeah. So we're a little bit behind in time, so as we change speakers, let's take a couple minutes so you guys say that. This is awesome how it all comes together. You might mention how you got your job when they asked you to write a WPS. You were the only
Oh
one
yeah,
who-
I had an interesting experience in my job interview. I sat down and actually my naivety helped me out in my job interview because I sat down and apparently like there's 15 other people that had applied for that same job and I was an EIT, so I wasn't actually qualified. They were looking for a full-time PN welding engineer. And one of the things that they asked me at the end of my job interview is I had done some summer work before, so I was familiar with welding procedures. But I sat down in that room and they said essentially, here's a data sheet, a blank data sheet, and they said fill it up. And I was kind of like shell shocked, and I was like, oh, I didn't really expect this. But I was like, yeah, whatever. Like, what do I have to lose? So I started filling it out. I knew some welding stuff. I knew some welding stuff from being in the lab. I knew what parameters would produce a satisfactory weld. So I just filled out the data sheet. Apparently, out of like the 16 applicants or whatever, I was the only one who actually filled out the data sheet, and that's what got me the job. So if it helps you out, study the data sheet.